Welcome to another video in my series of videos on control systems engineering. This is a short video where I'll introduce physical systems modeling. So it's technically not a control systems video, but you're trying to control something in the end, and a dynamic system basically. And so the thing to do is to first make a simulation of this system. The subtitle of this video is "What is an ODE?" And an ODE is actually the basis of your simulation. ODE stands for Ordinary Differential Equation. So first we'll talk about systems modeling. What a system model is you have a physical system. It could be a mechanical system or an electrical system, and you make a model of that system on your computer. That is, you're making a simulation of that system. You need this in order to design a controller for the system, and the reason for this is that you can put the controller on the simulated system and test it out and get it to work the way that you want it to work without actually having it initially on the real system. This is very advantageous because you won't break the real system. You're able to get the controller to have the properties that you want it to have without doing any damage to the real system. And you can actually even run the simulated system into areas that you normally would not run the real system into because of the danger of damaging that real system. Now, what type of systems can you represent? They can be mechanical systems, electrical systems also, fluid power systems, that's with hydraulic hoses and cylinders and pumps and motors and things like that. Aerodynamic systems, which airplanes, for instance. And there are many other examples. Almost anything physical that changes over time is a dynamic system, a physical dynamic system, and it can be modeled using techniques that I'm going to talk about here. A physical system also does not necessarily need to be simply in one domain like purely mechanical system. You can have cross-domain systems. You can have electromechanical systems, electrohydraulic systems, or even 3 or 4 domain systems where you cross these various domains with your real system does that. And basically what happens is that the simulation of the physical system captures how the real system behaves. So you need to learn how to make a model, a computer model that mimics the behavior of the real system. Now, what you do, or how you get this, is that you apply physical principles to certain situations, and they deliver equations of motion that govern that system, or governing equations they're called sometimes. Examples of this for mechanical systems: you implement or you apply Newton's second law to the system. For a hydraulic system or a fluid system, say a tank system, you might apply mass or volumetric continuity to that system, which basically says that the change in volume of material in a tank, for instance, is equal to the input flow rate minus the output flow rate. And then Kirchhoff's voltage law would be a physical principle that would be applied to an electrical system. And what we get by applying these physical laws is we get an ODE, or even a set of ODEs that capture the system's dynamics. Basically, what you're saying when you write these equations is you're saying that this system must obey these physical principles. And that delivers ODEs, which are ordinary differential equations. An example for a mechanical system: if you apply Newton's second law to a mass damper spring system, you get an equation like this. This is called an MCK system because you have a mass, you have a damper, you have a spring, and then also you can have an external force applied to that mass. This would be the volumetric flow in a tank, and it expresses that principle that I mentioned before, that the a rate of change of volume in the tank is equal to the input flow rate minus the output flow rate. And then Kirchhoff's voltage law is you go around the circuit and add up the losses over various components, and that has to come out to be equal to 0 when you come back to the same point that you started from. This would be Kirchhoff's voltage law for an LRC circuit. Now, as I said this before, ODE stands for ordinary differential equations. And let's look at these equations as a group. Now, I haven't shown how you actually get these equations. Those will be subjects of other videos, but we want to really look at the result here and what form it has, what the format is of these equations and how they represent the dynamics of the system. So let's look at that. On the left-hand side of all three of these equations, you have what's called a state variable. And so on the left-hand side, for instance, in the first equation, our state variable is x, which is the position of the mass. We're going to do this in a minute, this particular example. But I also have the velocity of that mass, and I have the acceleration of that mass over here. So over on the left-hand side, I have the state variables or their derivatives. And then also I can have physical constants in the equation, so they don't change with time, are over here on the left-hand side. And that's true of all three of these equations. Here the state variable is delta A, which is the change in height of the tank. And this is the rate of change in height of the tank. That's the velocity of the tank level as it goes up or down. Here on the bottom, we have the velocity across the capacitor, the rate of change of velocity across the capacitor, and then the rate of change of the rate of change of the velocity across the capacitor. So anyway, all of these have the same form. You have a state variable and its derivatives on the left. And then on the right-hand side, you have the exciting input, the thing that makes the system move. So, for instance, if you applied an external force to your mass, that would make the mass move, but it just doesn't move freely. It also you also have to take into account these other things that are hooked to the mass, and then your driving quote-unquote force in this ODE is the change in flow rate into the tank. And here at the bottom for this LRC circuit, the driving quote-unquote force is the voltage source in the circuit. Okay, now once you have these ODEs, you can put them into a computer program, and the computer they're numerical solvers for these equations. So with these ODEs in hand, you have your model, and then you just need to learn how to use whatever software you're going to use to simulate it to make your model. So anyway, I've already said this, so I won't go through it again. Let's look at one of the examples, and this is of a mechanical system. I'm a mechanical engineer, and so this is one of my favorite, well, it's sort of the archetypal example for a mechanical engineer. And we're going to look at this MCK system as a quarter car suspension model. So if you're designing the suspension of a system, this is the model that you would start out with. You basically get the car and you split it into 4 pieces, and you get each one of those pieces and you put a shock absorber and a spring underneath it. And so you would start off, well, we'll see. Let me just continue with this and we'll see how this works. So this system here actually will tell you how the mass would behave if it were mounted on the shock absorber and with this spring. Now, I've already said this, but this is the model that you initially used to design the suspension system for a car. The mass, M here, it represents the mass of a quarter of the vehicle. The vehicle has 4 wheels, and if the mass were evenly distributed on those 4 wheels, then you would use a quarter of the mass. If it's not, you'll have to take that into account and basically use the amount of mass that is above a particular wheel or shock absorber and spring. C is the damping constant for the shock absorber, and then K represents the suspension spring. Now, well, I don't know if I said this yet, but you don't have any control over the mass. The mass is determined by the people designing the car. It depends on how big the car is, what the car is made out of, how it's going to be outfitted, how it's going to be loaded, etc., etc. So you don't have any control over that. What you normally want to do is we solve a simpler problem first. We don't design the shock absorber and the spring at the same time. We take the shock absorber away and focus on the spring to start out with, and then we add the shock absorber. The shock absorber is sort of an afterthought in a way. The first thing to do is focus on designing the spring. So if we take the shock absorber away, we now have an MK system, as shown here. We don't have a force. I didn't mention this before, but there's no external force on a car other than the weight. Well, we can talk about that later, but you don't go down the road and then all of a sudden have a force applied to the car. So that external force goes away. That simplifies the equation. So if we apply Newton's second law, N2L, to this MK system here, we get this equation of motion, which is just a simplified version of the equation that I gave before. We have no C. We took the shock absorber away, so C is 0. And then the other thing is, like I said, we have no external force. Now, what we try to do as our first step is we want this suspension, this mass, to oscillate at a frequency of about 1 hertz, 1 cycle per second. And this has to do with human factors. Humans are used to 1 cycle per second, 1 hertz. For instance, your heart beats at about 1 hertz. Not exactly, but in that neighborhood. And when you walk at a pace of about 1 step per second, 1 hertz. So humans are built to feel comfortable with an oscillation of about 1 hertz. Okay, that's the end of this video. All I really wanted to do was to explain what ODEs are and that they're the basis for simulations. And so in another video, we'll look at how you make those simulations.